Please consider the following.
Hello, and welcome to our show, Gill Nye the Science Guy. I'm your host, Gill Nye, and this is Chris, my lovely assistant. Today we're going to be talking about bacterial resistance.
Patients dying of deep-seated infections were treated with penicillin. Many recovered completely in a few days, and news of the new wonder drug spread around the globe.
A key component to bacterial infections is drug resistance. I'm going to discuss the physiology and the biochemistry behind drug resistance. It is key to note that although bacterial infections aren't always severe, they can become complicated if untreated or if the bacteria becomes resistant to an antibiotic. To explain this are these sprinkles of dolphins. So these are both the same bacteria. What happens is we add the antibiotic and it kills part of it. Either the patient does a regimen that isn't complete or the bacteria mutate, so then part of it develops this resistance. So what happens is when you add that same antibiotic, it doesn't have any effect and the bacteria keeps on proliferating. So that's a problem.
This increase in antibacterial resistance has led to a need for new antibacterial compounds. I will demonstrate one way that researchers have found these such compounds. First, the researchers made a gelatin medium. This is great for growing bacteria. Then the researchers infected it with some bacteria. Delicious. Next, the researchers went out and they found some dirt samples that they thought might be promising. That's probably enough. The researchers then let this grow and saw what bacteria died and which ones still survived. They then took samples of where the ones died and they found the compounds in there that would kill the bacteria. Innovation tastes like orange. Normally in a cell, it creates the cell wall by forming different monomers together. These monomers are created from lipid 2 and lipid 3. These monomers will then stick together to create a healthy cell wall. However, with Texiobactin targets lipid 2 and lipid 3 to make sure that these cell wall monomers are not in the same shape. They can then not stick together. This causes the cell, represented by this balloon, to lyse. So now you're wondering, kids, how is Texiobactin different than other forms of antibacterials that target cell wall monomers? Well, Texiobactin is the first in a new class of lipid 2 binding antibacterials, which is a precursor to peptidoglycan. This is similar in how vancomycin works, however, it is effective against that vancomycin-resistant gram-positive bacteria, such as pneumonia or tuberculosis, due to the fact it also binds to lipid 3, a precursor to teichoic acid. Ugh. This is supposed to be resistant to all these different forms of antibacterial resistance for at least 30 years, is what researchers think. Thank you for joining us on this episode of Gill Nye the Science Guy. Today we've learned a lot about antibacterial resistance, Texiobactin, and how researchers find new drugs. Now remember, kids, wash your hands, don't pick your nose, and join us next week to learn about the wild world of oncology drugs.